thank you for the invitation to give a talk here. I had a look at the schedule, lots of talks in Korean, and I'm sorry that I don't understand the language, so I didn't make an attempt to join earlier. And so for me, it's a little bit strange to give a closing talk where I don't know all the presentations that happened before mine. However, I've been following this KpqC competition very closely, and also the two NIST competitions, the NIST competition starting in 2017 and the current NIST competition with the on-ramp signature schemes. And so I figured I will give a presentation about the comparison of those ones. So let me start with the NIST competition. So the attack timeline, well, that gives you already some idea of what I will be focusing on. So the deadline for the NIST submission was 30th of November 2017, so almost 6 years ago. So at that point, NIST had put out a call saying we would like to see some systems for signatures as well as for CAMs. And well, it is not a surprise that they, after they received the submissions, they first did a sanity check on these submissions. So in the end, they mentioned they had received some 82 submissions, but the world only ever saw 69 of those. So when you're seeing month 0, meaning, well, it's not even yet announced, that is because NIST was busy with, well, doing sanity checks on their systems. However, some submissions themselves said, hey, look, here is my submission, and here is a web page where you can see something about it, like e-print papers starting to appear or people announce on Twitter. And so, well, we felt inspired to look into this, and we were happy to be the first break of something which was submitted to the NIST competition. Now, break, I should be careful. There are lots of different types of break in this talk. So in this case, HeLa 5, which is a lattice-based system, had made a claim about CCA security. So claims that even if the attacker can interact with an oracle that gives decryption of random ciphertexts, that it would maintain security. And well, we showed that for HeLa 5, as submitted, there were reaction attacks. So it's not breaking the mathematical primitive, but it is breaking the crypto system. And we showed with scripts. So when you see that there's a script, that means that there is some attack which was really performed. It is within the normal computable time. So it's not an attack that says, oh, instead of 2 to the 256, you only have 2 to the 240. So very, very large number to slightly smaller, very, very large number. Those are also attacks, but they're far less devastating to systems. Whereas something where you're seeing a script where somebody was able to run, well, Python or C code to really break something, those are stronger attacks on the systems. Okay, so timeline, 30th of November was the deadline. Already in December, we're seeing some attacks. And then on the 21st of December, so nice Christmas present for those who have time over Christmas, NIST posted the 69 complete and proper submissions. So for that one, they were going, okay, these ones really fulfill the submission criteria. No claims about security. I think for some that NIST broke internally, they informed the submitters and the submitters withdrew. But there were also some, as you will see as I go down the slide, that were fairly easy to break and still were posted by NIST. This was a very big competition. It was the biggest that NIST had run at that point, 69 submissions being posted. Big step up from something on the scale of 30 for the SHA-3 competition, something like 16 for the AES competition. So yes, you can see it, it doubles for each competition. Okay, so when you look at what was in the mix there, NIST was saying, well, you can submit anything. For instance, we submitted class McLeese. Now we had done some work on class McLeese to take it from the 1978 submission to a modern scheme. We added a CCA transform, but basically it was McLeese's system with Niederreiter transform. But we could submit it because there was an option to submit, well, established schemes. And well, if the original designer didn't want to submit it, other teams could submit it. However, there was also a heavy emphasis on the performance already in the discussions people had to, well, I mean, in the round one, people had to submit C code. There were possibilities for updating the C code, and many teams did update the C code, no question there. But if I look at the submission portfolio, there were lots of, well, interesting designs, and very few had a focus on being conservative, on being sort of boring. And well, you'll see in a moment how that went. So same evening, a student of ours, Lorenz Panny, posted a script breaking Guess Again, which was the encryption system. And then 2 days later, we posted three different scripts having 4 different attacks against Rakos. So there was a signature scheme going down very quickly. And then other people, well, first Lorenz Panny broke RVB, and then other people jumped in. We broke HQ17, KpqC broke some McNee, which is a code-based submission. He also broke again. This is the kind of break where the security level gets reduced. It's not fundamentally broken. It's not like a polynomial time attack. So for Guess Again, there was no chance of repairing it. For Rakos, we thought there was no chance of repairing it. In the end, the designers did repair it, sort of. And they said that the keys after repairing would be several terabytes. So, okay, those are attacks where the system gets really broken. For McNee and for Lepton, the security level decreased, meaning the designers had made a claim for this much security. And after the attacks, which are theoretical attacks, the security is lower, but still too high to actually have a script. Okay, so still in 2017, Bart Bühlens jumps into DME, and then in the next month, we continued with some attacks on it was an Octonian-based system. There were like lots of different systems. Okay, so PQC RM is one which we will see reappear in the KpqC submission. So Alperin, Sharaf, and Perlner showed for this code-based signature system that they could recover a certain structure. And so they had a practical attack to show, okay, from the signatures and from the key, you can recover the secret key. SRTPI was something which was multivariates, but turned out to be univariate. And there's more things breaking. Sometimes, for instance, DME you're seeing here appear for the second time. So also in the NIST competition, some designers changed their system or didn't accept an attack. And so there were further breaks. Some design teams said, okay, we're withdrawing, we accept that this is really an attack. But some systems, Walnut DSA, which will appear many times, was sort of the worst offender in trying to patch and still get broken each time. Now, I should also highlight at this point that NIST had not said that they would consider tweaks. So there, it's basically one strike and you're out. So if there's any real attack on the system, it was pretty clear that NIST would discard it. That doesn't stop teams from saying, hey, look, I could fix it. And sometimes, yes, if it's a tiny little thing, like with the HELA 5, I wouldn't say tiny thing, but he just said, oh, we don't claim CCA security, so our attack didn't apply anymore. Such things NIST sort of permitted. All right, so here's the first appearance of Walnut DSA, which was a non-commutative group signature non-commutative group system signature system, and well, they got broken in so many ways. So here's the first one, and Bühlens attacking the same next day another version, and he will break it again. So in month one. Look, now in month 2, so it's February, we're seeing more attacks. Later was interesting in that it was a code-based system, and it was on the edge of maybe being too interesting, but also it survived longer than other code-based systems that had attacks. Okay, so rank sign, so that was the beginning of rank metric codes having problems. More Walnut DSA problems. So you're seeing that this is an example of something where the designers sort of didn't accept the attack, but still they get broken with scripts or well, very strong reductions. Okay, so flipping through this, you're seeing there's a lot happening in the NIST competition. Over the first few months, okay, we have now reached June, so more than half a year passed, but you're seeing 3 pages full of attacks. So there was quite some onslaught. I mean, it shows that there was a lot of attention, but also that there were lots of designs which were premature, that they were not yet ready, or they didn't have a solid security basis. And so at the end of year one, so a little bit over, end of January 2019, NIST announced the round 2 candidates. So out of those 69, they selected 26 second round candidates. Now there were 13, which I would say were really, really broken, and they didn't select any of those, so that's good. But they did select 3 of the 9s which had disproven security claims. So for instance, if you're taking HeLa 5, they had a security claim of CCA security, and we showed that CCA security was not a given. But that didn't stop NIST from accepting it. Actually, HeLa 5 merged with another submission, which was called round 2. And so, well, you're seeing at the bottom, there's 5 merges. So you're seeing 3 out of 9 plus 28 out of 47. So that would be 31 minus 5. So that's the 26 second round candidates. So they didn't pick any of the broken ones, but they were sort of lenient with systems which had disproven security claims. So if there was an attack, if there was a script, they were out. But if there was some claim of, well, CCA security, but they only achieved CPA security, then NIST accepted some of those, not all of those. There were 6 unlucky ones where NIST wasn't as lenient, and there were 3 where NIST was like, okay, well, let it pass. In general, there were some, in particular in these 28 out of 47, you're seeing there's quite a few, 19 submissions which didn't have any problems, but they were still discarded. And so there was a bias towards submissions that were faster, more performant. So NIST was grouping similar systems together and saying, oh, you 5 are about the same, these 2 are faster, so those 2 proceed to round 2, and those 3 get discarded. I'm being very careful here in what I'm saying. It's really faster, and they're saying it's similar. So they're not saying, oh, but these have more security. So for instance, there was one system called Titanium, which was based on lattices. And it had this interesting design feature that they were saying, well, if there's any problem with any of the ideal lattices, of any of the structured lattices, then this would be the most secure because it would cover sort of everything. Now, they took one which had a similar advertisement, namely Frodo, but Frodo is bigger than Titanium. So there was some trade-offs that they're making where if one would have taken everything which is good and secure, one could have promoted more of the systems. And some of those choices didn't actually go so well for NIST. Okay, so looking into round 2 and round 3, so attacks keep getting better. That's a general thing. Attacks can't get worse. But for instance, in 2019, we started seeing lots of attacks on, say, the approval security. So MQDSS was a system based on the hard problem of multivariate quadratics, and not one of the systems which had a trapdoor, but a rather sort of boring system. However, in the change from round 1 to round 2, they had changed their parameters. They had gotten too optimistic, one should say, in hindsight. They halved the parameter sizes, saying, oh, we over-designed. We don't need this big parameters. We can do with half the size parameters. And then Saroja and Kales showed, no, that was too much. Actually, the security proof had a gap, had a tightness issue, and they would have needed 3/4 of the original. So the round 1 submission actually stayed secure. The round 2 submission got broken, but something in between would have been okay. And of course, the round 1 submission would have been okay. There were many more similar attacks. So for instance, QTesla got attacked based on their security claims. So there are, well, several systems where security claims were disproven during this. Not so many systems where there was really an attack. So most of the systems where attack scripts were found were in the first round. So here you're seeing only 2 broken submissions. So systems where there was a very strong attack. Then 5 submissions where the security claims were disproven, but from round 2 to round 3, NIST eliminated all of those. And then they promoted 16, of which 1 was a merge, so there are 15 round 3 candidates. Okay. And you would expect that after, well, a turbulent round 1 and then a round 2 where they're going for the smaller, for the more secure ones, that there wouldn't be much happening in round 3. It would be more a consolidation that, yes, the selections they made in round 2 would be good. But that didn't quite hold so. So looking at the NIST report, I'm highlighting one candidate, namely Rainbow, and that system, the report was saying is, the key point here is not that attacks have improved and may continue improving against Rainbow. So they had some warning words, but they were also saying, no, we are pretty confident that everything is fine. And they continued saying the theoretical analysis has been tightened in a way that matches the empirical observations in the generic algorithm. So my reading of this is that, yes, NIST saw the security of Rainbow getting scratched, but that didn't worry them because they had some ideas of what they would be expecting in reality, like empirical analysis. So this was September 2020 when they did the round 3 announcement. And so, well, actually then Budens did attack Rainbow and reduced the security levels beyond what NIST thought. There were also interesting comments about swings in the round 2 report, where NIST was going like, yeah, well, we didn't put swings as a finalist because we have better schemes. So the Rainbow was a finalist and swings was kept as a kind of a backup. Yeah, we don't see anything wrong there, but, well, we wouldn't want to have to use swings was sort of the tenor. Okay, so then Budens in October broke this. There was an interesting fight between different MQ systems. So Rainbow lead designer is Jintai Ding, and then Jintai and 2 colleagues, Tao and Ding and Petzold, took a swipe at GEMS, so another multivariate system in November. And then, oops, in February, Bart Budens actually posted a script which breaks the smallest Rainbow system. So this was the beginning of announcements of something that is breaking a system in a weekend. So he actually showed how to break the Rainbow parameters. And with that, so Rainbow could try, of course, to update the parameters, but for this round 3 scheme, NIST was going like, no, this is not good. So eventually in July 2022, NIST made an announcement. Out of those 15 round 3 candidates, they selected 4 of them, 1 chem, namely Kyber, and 3 signature systems, Dilithium, Falcon, and Swings, which they say they would want to standardize. Let me fast forward a bit. So this summer, so August 2023, they finally posted some draft standards. So it is really not yet standardized. We're only now in the draft standard phase. So you're still in the comment phase. And if you look, you're seeing lots of comments on the NIST post-quantum mailing list coming in, finding errors in these specifications. In particular for Kyber, there have been lots of changes by NIST. And, well, now there have to be lots of fixes. NIST also put out a round 4 where they put in 3 code-based systems, Bike Classic McLeese KpqC, and Psych, which was an isogeny-based system. They also said, well, yes, we're having already 3 signature systems, but we would like to see more variation. So Dilithium and Falcon are both based on lattices. Swings is based on hash functions. And they were asking for more signatures. They were sad that Rainbow was broken. Rainbow had this unique characteristic that the signatures were very short. The public keys are very big, but it had short signatures. And they call for new signature systems highlighted that they would like to see something with a similar profile. Well, okay, so I said July 22, so let me dive in a little bit. On the 5th of July was actually this announcement. And no 30 days later, so on the 30th of July, KpqC posted an attack, and there was a huge onslaught on Psych. So Psych, which had been designed in 2011 and held up for, well, 11 years, suddenly got broken and got broken worse and worse and worse and worse. Now, several of us had warned that there might be some concerns about Psych, but also none of us really had any insight, had any idea of how to really work it. So Chloe Martindale, who was a postdoc with me, and Lawrence Punny, at that point PhD student, they even wrote a paper about all their failed attempts and all the failed attempts in the community to break Psych. But KpqC found a way that hadn't been considered, and suddenly Psych absolutely crumbled. And it's interesting, different communities. So in the isogeny-based community, everybody jumped in and helped to really find out how broken it is and how much this attack applies to other systems. Well, this also led to quite some publications. So 3 papers at Eurocrypt, including the best paper this year, and the other 2 got honorable mentions. But to show you what I mean by really broken, so here are some timings. So the original submission, so the KpqC announcement that they had broken all these Psych parameters. I mean, something which runs in 6 minutes is really, really broken. And for the largest security level considered, it was just 20 hours. However, with the community effort that they put in, they got it down to 1 hour for the largest and just 2 seconds for the smallest. So there was the work in the next few months made those attacks even more powerful. Now, NIST had some comments how their understanding of Rainbow had greatly improved over the past years. And so, well, one could paraphrase this for Psych that our understanding of the concrete security had greatly improved over the past days, but not in a way that one wants security understanding to improve, because it got totally broken. Okay, so this is sort of ending the NIST competition. I mean, it's still going on, but ending my review of the NIST competition on a fairly low end. That's something which had been through so many rounds, got badly broken. On the other hand, it's also a success of the scientific community to have found this attack and to then really try to understand how bad this is and how wide it spreads. So jumping into the KpqC competition, much more recent submission deadline, as all of you know better than me, was just a year ago. And I would say there were lots of differences between the NIST competition and the KpqC competition. So first and foremost, I mean, KpqC is a Korean system, a Korean competition. So you had a restriction that only teams with Korean designers may submit. And I understand why you would have this restriction, but of course it also changes the composition of what expertise a country has, then determines what systems get considered. And compared to NIST, who was going for, well, we're totally happy to take a boring system from the 1970s. Yes, you may submit even if you're not the designers. KpqC added a criterion of originality. So you're really wanting to have something that is designed by the people who submitted. And again, I understand where this comes from, because if it's, well, public money sponsoring competition, you want to analyze what your people bring to the table, and you want to analyze the new things and not redo the work that has been done already. I think this ties in with the focus that is stated for KpqC, namely the expertise building. I mean, workshops like these or summer schools that I heard you've been having are helping to build expertise. And with that in mind, it makes totally sense to say, oh, we want this to be new systems. It is a different focus from saying, oh, we must, as soon as possible, migrate to post-quantum, and we must use the most secure system, because then you would also consider the NIST competition results or other submissions. But if your focus is on building local expertise to build an ecosystem, then yes, that is very important. And I also really liked, not as an evaluator, not as a person who has to read all the new versions, but I like as the approach that teams can update their submission, that they can see, we learned something here that we didn't know before, but it doesn't fundamentally break the system. We misunderstood some bits, and here's how we can fix it. For systems where that is possible. Now, also I liked that there was less focus on speed and implementations in round one. So NIST, in their selection from round one to round two, had a very strong emphasis on speed, and seeing less emphasis on this for KpqC. And I think this is good, because what we saw with NIST in prioritizing efficient submission or focusing on efficient submissions was that they fell flat on some of those, where maybe the slightly slower candidate with a more conservative design would have been a better case. And yes, I already commented on the new submissions when NIST wanted established systems. So that is sort of the counterpart to the regionality. So in NIST signature systems in particular, they were saying that they're really asking for established systems. When we get to it, you'll see that no, they didn't actually keep up with that. But still, from the call text, there are differences. That NIST says, well, please submit something that people have looked at, ideally already published some years ago, whereas KpqC was very happy to have fresh off the bat new systems. Okay, so jumping in. So here are the chem candidates for KpqC, and I'm just categorizing them by their hard problems, coming up with something which fits into just one column. I'm merging some systems together where you as designers might feel like, oh, they're very, very different. And then on the left column, I have comments if there was an attack. To be clear, for instance, for Smaug, there was no attack. I'm still highlighting that they updated the parameters, but it was not an attack. It was that the parameters were okay, even though they didn't consider the meet LW attack. For comparison, Tiger did need to update their medium, the 192-bit parameters in response to the meet LW attack. Okay, so going through those, so IPCC is a system based on graphs, and I know that there was now a talk, and I have no idea what the update to IPCC 7 is. We in Eindhoven had a look at the original and the updated version and came up with a text on both of them. For the first one was a message recovery, and for the second one, actually a key recovery attack. Also for layered rollo, well, the organizing team takes the first prize there, but we also did several attacks, but also the layered rollo team did update. So I've seen on the program that there was an update to layered rollo. I don't know whether this matches the last one on the mailing list, but I'm a bit concerned because there have been lots of attacks, including message recovery attacks, so pretty strong ones, and the other ones reduced the security back to the security of Rollo 1, which was, well, it was a NIST candidate up until the second round, but then didn't proceed further. Okay, I have a different, jumping past Paloma, I have a different feeling about REDOC. Now for REDOC, it's another rank metric code. So layered Rollo and REDOC are both rank metric codes. REDOC we broke in different ways. So we showed that the implementation wasn't correct, but we also showed by using generic attacks that exist already that the parameters were too small, that they didn't consider some of the attacks and therefore had to update the parameters. But we also see how we can fix it. And we don't see how to attack the fix. Whereas with layered Rollo, we saw lots of the fixes being attacked. We didn't have time the last few weeks, so we haven't looked at the latest version yet. Paloma, no comment, which is sort of, I tried. I mean, I'm feeling like Paloma, let me put this here. Paloma is very close to classic McLeese, something I'm intrinsically familiar with, but it has a different choice of the Gopper polynomial. And to me, I mean, we designed McLeese the way that we did because we think this is the best way to design it. And so, of course, I'm seeing the burdens of this other polynomial because you need to adjust how Patterson decoding can work. You need to work with a much larger field size. But also there is the boon, the benefit of having a simple description where all field elements are used. And I have not found any attack where this different choice makes a difference in the security. So there's a big white space there. For Entroplas, the only thing that we have seen, and not by us, was a CCA attack, and there is a fix where we're still thinking about whether we could maybe do some reaction attack. But at this moment, yeah, clean bill of health for Entroplas, clean bill of health for Smaug and Tiger. So Tiger had more bumps in their road, so they had the meet LWE attack where they needed to update the parameters, and then the updated parameters, they miscalculated the decryption failure probability. There's now a version 3.0, or maybe there's now 3.1, I don't know, where we don't see these issues anymore. And both Smaug and Tiger, they are very similar designs to Kyber, but both are better than Kyber. Both are smaller and faster than Kyber. If I compare this with NIST, they only have one single cam selected and 3 more in round 4, because, well, Psych is gone by now. So I'm happy to see that KpqC is calling for cams, because to me, the cam migration is the most urgent part. I mean, we need cams in order to get confidentiality. And confidentiality is the issue that an attacker might record now the traffic, so store encrypt the traffic, and then try to decrypt it later. So it is super important for all confidential information that you upgrade to a cam. And so I'm happy to see that you have some secure cams in here, and that you're considering cams, even though NIST is sort of not interested in more cams, didn't call for more cams. And also, well, seeing that Smaug and Tiger are much faster and smaller than Kyber tells me, oh, there is actually something to be gained. On the signature side, here I did give up on trying to fit everything into a single row, because, for instance, for AIMER, I could categorize it as an MPC in the head or as a symmetric system. So for the NIST competition, they always had Picnic in the symmetric one together with Sphinx, and AIMER is similar to Picnic, or, well, in advance of Picnic, but has a different block cipher on the internal. So Picnic used low MC, and AIMER is using the AIM block cipher, a new design which is sort of more aggressive, or having lower lower multiplication count than low MC. Now, there were issues. So 2 teams have found attacks on the AIM block cipher because the exponents were too small. On the other hand, when the exponents are too small, you can increase the exponent. And in the metric of AIM, that doesn't increase the cost of the most expensive part. There was also something in the feed forward which needed to be fixed. So with the fixes with AIM 2.0, we're not aware of any attacks on AIMER. On the other hand, well, it's a very new design, but it's also the only one in this MPC in the head / the metric in the KpqC competition. Enhanced PQC RM, I mentioned PQC RM in the NIST competition as having had an attack. Enhanced PQC RM also got submitted to the NIST on-ramp competition. You'll see it also on the next slide. And there 2 attacks have been posted. One with an attack script by Debris Alassar and Vasseur. And that one shows that with enough signatures, the secret code structure leaks. So it brings the attack, well, it brings the system back to what was broken in the NIST PQC, the first competition. There has been an announcement of a second attack by the NIST team, but we haven't seen any details of that. But we did go through the attack. We sort of reverse engineered how the attack works from the script, and we ran the script, and yes, this does break the system or reduces the system to the original one. For FIPS, it's based on isogenies and has a very much Sphinx-like structure. So the details of how the system works is really like FIPS, like Sphinx, but they changed from the SHA-3 or SHA-2 hash function to an isogeny-based hash function called CGL, named after Charles Gorin Lauder. One problem is that the hash function is very, very slow as far as hash function goes. But to me, another problem is that this hash function is not too well studied, because it's always been like this sort of, well, it's a provably secure construction with a math design, but it's so slow that it's not very attractive to be used. And so in particular, the security properties necessary for FIBS or for the Sphinx design have not been studied for CGL, some of the properties. So collision resistance has been studied, but the decisional second pre-image resistance that Sphinx also requires has not been studied for CGL. But I think the bigger problem is that it takes 3/4 of an hour to make a signature. Going a bit faster, so there's a clump of ideal lattice ones. I understand that GCK sign is saying, okay, well, we're actually based on the GCK problem, correct? But it's, if I'm going for big categories, it's very close to ideal lattices. And also in the attacks that we've seen, so the module sys problem is coming in, and then the TMO analysis. So GCK sign had sort of misestimated taking a sparse system for something which would be dense. And so their system parameters are much less secure. Similar issues with Peregrine. So there were an improvement over Falcon, but by the way that they're sampled, they ended up missing a rejection sampling and thereby leaking the private basis of the lattice. Very recently, there has been a posting of an attack to the KpqC mailing list. We had analyzed the attack and confirmed that it worked even before they posted it. And yeah, now you can see the exact details of how many signatures you need. And then MQSign, that is taking the multivariate systems, which is sort of established, and then changing the systems to have smaller keys. So changing, there's some matrices running around and going for sparse versions, so fewer entries in these systems. And the sparse versions of the MQSign have attacks. There are 3 empty blocks, so Hete, NCC sign, and Solme. All 3 are based on ideal lattices, some of those modules, some of those ring LWE. And for all of those, we didn't see any attacks. Hete and NCC sign in the structure are very close to dilithium, and Hete has the benefit over dilithium that the signatures are shorter. Solme is close to Falcon. Now Falcon is already there and has been selected by the NIST competition, but it's worth pointing out that NIST has not posted anything about Falcon. So there's still no draft specification of Falcon because Falcon is very complicated to implement. And Solme is close to Falcon, but removes this problem of being hard to implement. So Solme is sort of an improvement on Falcon, not in the properties that it's faster or shorter, but that it's actually possible to implement it securely. So the distribution of systems is only 1 code, 1 isogeny, 1 MPC in the head or symmetric, and 1 MQ, and then 5 lattice-based systems. If I compare this with what is happening currently with the on-ramp for signatures, I'm not going to go through this one. So this is the latest competition where the deadline was just in June this year. So this is the NIS count. Okay, similar numbers for isogeny based. In total, they have 40. So actually even fewer isogeny based. 5 lattice based, which is proportionally less, but then 6 code based, 10 MQ based, and also a large number of MPC in the head and symmetric based ones. So if I look at the comparison, then they have many more multivariate systems and many more, well, this MPC in the head is a relatively new paradigm. The top one, the 7 ones, are based on hard mathematical problems. So for instance, you have several which have an M in their name, which are based on the MQ problem, but not with a trapdoor, but with this MPC in the head. And so I sorted them under that category rather than in the MPC category, rather than in the MQ category, else MQ would have been even larger. But also if you look at the parentheses about attack issues, attack analysis, some bits lost, there's a lot happening. So proportionally, I think the NIST competition also has many more broken systems. So just to summarize, I think we started 10 minutes late and it's almost used those 10 minutes now. So to summarize, I think the KpqC competition has a very nice portfolio of alternative schemes. I mean, you aimed for new schemes, you aimed for something which is different from what the NIST competition has been doing for 6 years. And that led to several nice designs. Several designs were, well, we don't know how to break it, and also where we're seeing the benefits of it. One thing I found striking is to see all the improvements over dilithium, falcon, and kyber. These are standardized or chosen for standardization by NIST. NIST has said, okay, these are ready. And I remember at some point in the NIST competition, there were arguments, well, made by people, in particular Vadim Lubashevsky, who is on all these 3 teams, saying, oh, we really shouldn't standardize NTRU because NTTRU is much better than it. We have now some improvement over NTRU, and so we shouldn't take something where we know how to do better and standardize it. Now, seeing the KpqC competition, I'm feeling like, oh, we also have strong improvements over dilithium, falcon, and kyber in implementability, in speed, in size. So is standardization always too early? I don't think so. I think we need to standardize at some point, but it is interesting to see the creativity and the new ideas that went into making the designs here. So particular, I mean, Hetty with getting the signatures shorter, Solmi fixing Falcon, and Smaug and Tiger improving on Kyber. And then for the rank metric codes, yeah, both in the NIST competition as well as here, we've seen that there is still issues in code-based signatures in particular, but also in some encryptions. And I mean, if you listen to Alex Pellegrini's talk back in July, you might have felt like, okay, we're bashing Redoc, there's nothing good there, but actually we're now thinking it might be okay after the fixes. So it is different in, yeah, it's targeting a different regime. So when you're looking at how all these attacks unfolded on Rollo, so Rollo in the round 2 is a merger of 3 different rank metric based systems that were in the NIST competition in round 1. And they were going for systems where the length of the code is larger than the exponent of the field. So they're all working with F2 to the M, and their M is smaller than N. Whereas Rollo is in a range where the length is N is smaller than N. And that means that the attacks that were found on Rollo, well, of course they apply, and some things did decrease the system parameters or the security of the system parameters a lot, but it is not as devastating as we've seen with with the Rollo versions in the NIST competition. So it is something to be cautious of. I wouldn't want to have any sensitive data encrypted with it, but I find it interesting that there is now a state of a rank metric-based system which we don't know how to break. So, well, maybe next year we know more, maybe positive, maybe negative. Same for MQ systems. So we have seen in the NIST competition how Rainbow and GEMS, which were, well, and before that, there was also GUI and LUV. So those 4 systems were in the NIST competition as multivariate systems, and all 4 of them had issues. Here, MQ sign, 2 out of the 4 systems are broken, and for the 4th system, for a 3rd system, there should be a posting soon with also some considerations of, well, there's more structure than necessary or than good. At the same time, the core systems, so plain OUV or plain HFE should be okay. And we've seen this also in the NIST competition. So looking at this corner of MQ systems, there are some which are like scooting ahead and being way too optimistic. And then there are some which are like in the boring regime. So starting with Mayo, these systems, we don't know any attacks. And so also on the fourth corner of the MQ sign system, which is very close to the visual OUV, that as a core system seems okay. So if you're looking for a secure system where you have a very short signature, this seems, yeah, we don't know anything for the last 20 years that breaks this. So I'm trying to close on an uplifting note because I think there's a lot of potential in the KpqC competition. Some designers will be disappointed in the round two. I might not see my favorite submissions in round two. I don't know what KpqC will be deciding, but I found it very interesting to take a look at this. We did, as an Eindhoven team, we did write a report which we plan to post on ePrint and on the KpqC mailing list very soon. We still have one issue to solve where we want to inform some people before we post it. With that, I thank you for your attention.